When you think about the dangers of electrical work, the first thing that probably comes to mind is, getting a shock. But there's another hazard out there, one that is way, way more than just a simple shock. It's called an arc flash. And we're not just talking about a bigger spark here. This is an event with some truly terrifying power. So understanding what it is, that's the absolute first step to respecting it, and more importantly, preventing.
Okay, get ready for this. 4 times hotter than the sun. I mean, just let that sink in for a second. An arc flash can hit 35,000 degrees Fahrenheit. The surface of the sun, that's only around 10,000 degrees. So yeah, we are talking about an instantaneous, explosive blast of energy that's just, well, it's almost impossible to wrap your head around.
So when you see a worker dressed up like this, they look more like they're about to walk on the moon than work on an electrical panel. You might think, is that really necessary? Well, it is not an overreaction. It is a direct response to that insane level of danger we just mentioned. So the real question becomes, what in the world is going on inside that equipment that could possibly demand this kind of protection?
All right, so let's get right into it. What exactly is an arc flash? It's a term you hear a lot, but when you dig into what it actually means, you realize it's a danger with a whole lot of different layers.
Here's the key thing to understand. An arc flash isn't just one single event. It's more like a three-pronged attack that happens all at once. First, there's a blinding flash of light. Then, you've got the concussive blast, like a bomb going off. And on top of that, it's throwing superheated molten metal shrapnel everywhere. It's a thermal assault and a physical assault happening at the exact same time.
Yeah, let's circle back to that number because it's just wild. 35,000 degrees Fahrenheit. At that temperature, solid copper doesn't just melt, it vaporizes instantly. Tools turn to liquid. The air itself transforms into this superheated, electrically conductive plasma. It's this extreme, mind-boggling heat that really makes an arc flash so devastating.
Okay, but here's something that might surprise you. As dangerous as the blast and the molten metal are, a lot of the time, the biggest threat actually comes after the arc flash is over. Think about it. That intense heat can set a worker's regular clothes on fire. And that fire, that keeps burning long after the initial explosion is gone. That's what often leads to the most severe and sadly often fatal injuries.
So, with a hazard this severe, you can bet that safety isn't just a suggestion. It's an absolute requirement. There's a whole system of rules and standards designed to protect people. So, let's take a look at who's setting these rules of engagement. Basically, it comes down to two main players. You've got OSHA, that's the government agency. They make and enforce the law. Then you have the NFPA, the National Fire Protection Association. They're the ones who write the super detailed standards. And for electrical safety, the big one, the one everybody, including OSHA, looks to as the Bible for this stuff, is NFPA 70E.
So, you've got this huge, detailed standard, NFPA 70E. What do you think the number one most important message is? It's actually incredibly simple, even if the process to get there isn't. It's all about one thing, turning off the power.
And this quote really nails it. The absolute best way to stay safe from any hazard is to just get rid of it completely, right? In the safety world, this is the golden rule, the top of what they call the hierarchy of controls. All those crazy suits and special tools, they're plan B. The number one goal, always, is to de-energize the equipment before you even think about touching it. But, and this is a huge but, turning it off is a lot more involved than just flipping a switch. NFPA 70E lays out a very specific 6-step process to create what's called an electrically safe work condition. You have to find every single power source, disconnect them, look with your own eyes to make sure they're disconnected, put on locks and tags so nobody can accidentally turn it back on, and then, and this is the most important part, you have to test it to prove there's zero voltage. You have to do all of that before it's actually considered safe. Okay, but we all know there are times when you just can't turn the power off, right? Like if you're troubleshooting a problem or running diagnostics. So what do you do then? Well, that's when you have to enter this whole other world of calculated risks and very, very specific safety boundaries. When you're working on live gear, you've got to imagine these invisible lines of danger around you. There are the shock boundaries, which are all about keeping you from physically touching something live. But then there's the arc flash boundary, and this one can be much bigger. It's the line where, if an arc flash were to happen, you could get a serious burn. Stepping over that line without the proper gear, that is a huge gamble. So what if you have to cross that arc flash boundary? Well, then you need protection. And that is where PPE, personal protective equipment, comes into play. It really is your absolute last line of defense when you just can't get rid of the hazard itself. But how do you know what PPE to wear? You can't just guess. You have to measure the hazard first. And we do that by calculating something called incident energy. The easiest way to think about it is like a dose of heat. How much thermal energy would you get hit with if you were standing at a certain distance? It's measured in calories per square centimeter. And that one little number, it determines everything that comes next. So you take that incident energy number and you use a table just like this one from NFPA 70E to figure out what level of protection you need. You can see right here as the minimum arc rating climbs from 4 calories to 8, up to 25, and then all the way to 40, the gear gets more and more serious. We're talking more layers, more coverage, the whole 9 yards. Okay, so let's put some visuals to those numbers. On the left, that's your Category 2 gear. It's rated for at least 8 calories. Now look at the right. That's Category 4, for a minimum of 40 calories. The difference is pretty stark, isn't it? You go from basically a heavy-duty shirt, pants, and a face shield to a full-blown multi-layer flash suit. The protection scales right along with the danger. But this is so important to remember. The suit, no matter how tough it is not the point. The goal isn't to wear the suit. True safety is all about building a system, a culture, where having to rely on that suit is the absolute last thing you ever want to do. And that brings us right back to this idea, probably the most important concept in all of safety, the hierarchy of controls. Just look at where PPE is on this pyramid. It's dead last, at the bottom. Why? Because it doesn't actually get rid of the danger. The best, most effective ways to stay safe are always at the top, eliminating the hazard altogether, turning off the power. That has to be the goal, always. So this all boils down to one final, really critical question we should all be asking. Is the safety culture where you are built on prevention, or is it just built on protection? Are we focused on engineering hazards out of existence, or are we just getting better at handing out bigger shields? The answer to that question, well, it makes all the difference in the world.